Great. Thanks for the nice introduction, Christoph. I hope you can see my screen, the main presentation screen. So yeah, Christoph already spoiled what I'm going to present today. It's about g.Pype, but for the beginning of the first couple of slides, I want to go a few steps back and motivate why we ended up developing g.Pype. So welcome to my talk, Python for Neuroscience. It's actually one part of my Python for Neuroscience presentation. So one more talk will follow on Saturday during the hackathon at 10:30 European summertime. There I will dive a little bit more into the real programming techniques and customizing your neuroscience pipeline using our tools. Today I want to stay a little bit more on the surface and giving a bit more context and motivate the whole project. So since I'm presenting Python for neuroscience, I should actually motivate why we use Python for neuroscience and why Python is so extremely popular for neuroscience experiments. So first of all, it has a vast ecosystem of tools which are available. If you're using Python, NumPy, SciPy, MNEPython, all those very huge and very powerful toolboxes. They're available and you can just install them and just use them. So it's an incredible resource for use and for basically any problem you have. There is probably a Python package available. It has a massive community, so I really underestimated before I dove into Python. I really underestimated how big this community is. So whenever you find probably a bug in some package, or when you have a problem you are unable to solve, you can be fairly sure that the community will be able to help you. Putting that together, it allows you to rapidly prototype your experiments. So you can use graphical user interfaces. You can program using Qt, for example, very effectively. You can implement real-time signal processing for your whole data propagation and acquisition chain. And you can also use sophisticated machine learning algorithms. You don't even have to code on your own because they might be available already. And putting everything together, this gives you a very huge potential to come to your goal fairly quickly. And it's also quite beginner friendly. So of course you need some experience in coding. You need if you're programming something that has some complex structure. So that will of course there will be some skills required. But when you want to put this into code and program it, it turned out that, at least for my experiments, but that's commonly accepted knowledge, I would say, that it's very easy to learn Python because the language is extremely structured, extremely consistent. So you don't have to deal with with messy structs. It's very very easy to start with. And also, with the rise of AI and use, AI also has access to all those open source and freely available documentation about Python. It's just so simple to start coding with it, to get an experimental script just maybe being generated by AI and just customize yourself. So this is a very huge motivation for that. And last but not least, it's very cost effective because basically all the Python packages, they're available for free, at least for research purposes. And most of them are open source for the most relevant parts. So this is perfect for research and coding communities where you don't have the barrier of licensing and paying huge license fees before you even can start with your design and experiments. Good. So having all this kind of high-level motivation points in mind, let us kind of sketch a very abstract neuroscience research setup. So what would be the requirements for such a neuroscience setup? So first of all, when you're doing neuroscience with EEG, you need a robust EEG acquisition system. So you need something which is reliable, where you don't have any connectivity problems, which you can set up easily, and so on. So that is a very huge leverage, a very huge kind of a need you have to fulfill when you want to do good neuroscience. So having such a reliable EEG headset, mainly you want to process your data, or at least pre-process your data in real time, right? So you want to acquire it, and you want to provide at least some feedback on the screen while the data is being recorded. And if you're doing science, if you're doing research, of course, you're not having one great idea and this will solve everything, but it's always an iteration. It's always trial and error. So you start with some experimental protocols and you see that, okay, well, let me try this one, let me try that one, let me change the stimuli. So you really want to customize your experimental protocols easily and without much effort. Maybe wants to increase the task length, or maybe wants to even try something completely different, but without too much effort. And you also want to have overall, even if you don't want to process everything in real time, you want to have something like a platform which is lightweight and powerful enough to process more complicated tasks. If you're interfacing a more extensive machine learning toolbox, for example. And overall, from the programming structure, or from the overall design, such a neuroscience research setup should be designed in a clean way, and it should provide modular interfaces. So the idea is not to do or to reinvent the wheel, to do what everybody else has been doing already. So not to compete with everybody and to try to do it better, but to complement each other. So use things which are already there and interface with those tools as cleanly as possible, but also provide an interface probably to other tools and modules which want to use your system. And also quite motivated by the Python way of development and designing and coding is, and also for the, to provide some scientific rigor, you want to make your experiments reproducible. So it's of course possible to perform an experiment with your setup, your customized setup on your machine with your subjects and on your location, but it should of course be reproducible on other locations, on other with other subjects, and also on other machines and PCs. So reproducibility is a huge factor for research in general, and neuroscience research in particular. And he also wants to keep your code as transparent as possible. So if you want to make your experiment reproducible, up to some degree, you have to share some code or some protocols. And here, for example, GitHub and the Python package index are just, the most prominent examples which just drive this spirit of code transparency and code sharing and reproducibility forward. Right, and one thing which is probably underestimated, but from would say a commercial standpoint, extremely important, and we have had contacts with companies in this respect a lot, is that when you're, for example, a spin-off from a neuroscience lab, and you have some assessment or some protocol which has been proven to be very successful for some certain task or some investigation. And you want to roll this out, you want to go into production, you want to deploy it, then usually those guys face substantial challenges, because the research world, the research, setting up research experiments in labs is something entirely different from encapsulating them into packages and deploying them to client PCs. So I would say such a neuroscience research setup should, of course, be very flexible for research, but it should at the same time be very robust for production. So the transition from research from prototyping to production should be as simple as possible. All right, so with those kind of high-level abstract requirements, we sat down and we thought, okay, some of them we already fulfill, some of them where we have the key expertise to fulfill them, and for some we still need some work to do. So we kind of wrapped it up and identified a few points where we are, what we can do, and where we want to get. So starting with, for example, efficient and robust EEG acquisition, probably the two most outstanding devices right now are the g.Nautilus, which is our wireless EEG headset and medically certified, and its pendant for the non-certified version, and with a couple of reduced specs, is the BCI Core 8, which is a relatively new wireless EEG device with 8 channels. And those two devices, they already have Python APIs, so we can actually acquire data via Python right away. Next thing is the experimental protocol. So we have Paradigm Presenter, you might already know. It's part of g.Hysys. So we are able to present stimuli in real time, provide extremely reliable software triggers, and to, with some coding experience, it's fairly straightforward to customize experimental protocols on the fly. So that's something we already have. Talking about behavioral feedback. So for many neuroscience experiments, you want to have some feedback, right? So it might be an eye tracker or a key press, some response from the subject to know what's going on is very valuable. And here we have also a couple of tools. Probably the most, the easiest example is just a key press, right? So if you have some reaction task, people should just, or some mental task, some cognitive task, and people should press keys depending on the stimuli shown, or memory tasks, whatever. It's very easy to map those keys to trigger values and to record them in real time alongside the EEG data. So this is kind of what we already have. It would be very easy to implement. And using those more conceptual aspects, we at g.Tec, we have developed quite a lot in terms of real-time brain-computer interfacing. So we really know how to implement real-time data propagation in a very robust and efficient way. So that's something not done, which had not been done in Python then, but that was a fairly small step with all the experienced guys we have here at g.Tec. And also putting that a bit further, node-based processing or block-based processing, probably those of you who have been seeing the talks with g.Hysys, or who have used this already, it's also something we have been doing for quite a while, in a sense that we are creating our signal processing paths with blocks or nodes, and each block is doing something, forwarding the signal, and thereby you can just very flexibly create your overall signal path. Good, so this is also something where we were quite optimistic to get to a solution fairly quickly. Right, and now then, kind of the challenges, or the way which was still ahead, and the things we wanted to achieve, because we have been asked quite frequently about that, is cross-platform support. So as you know, basically all g.Tec systems and softwares are mainly available on Windows. But since the neuroscience community is for large parts working on Macintosh, it would be necessary, of course, to provide at least the key features of such a neuroscience pipeline also on Macintosh. And a very important conceptual change, or transition we wanted to undergo, is to provide not a product, but a platform. So we want to provide something people can use to create their own experiments, applications, or even products, right? And the overall entry barrier should be as low as possible. So talking about interfacing. It should be as simple as possible. Talking about expenses, it should be as cheap as possible, or even free for the beginning, and stuff like this. So it should be possible that people can use it right away. And corresponding to the last requirement from the previous slide, it should be possible to create applications on this platform, but those applications should be almost production ready. So it should be only a matter of couple of maybe clicks or like automated processes to transform this prototyping application into a robust product which can be rolled out and deployed, for example, in a commercial setting. Right, and you can see a big hole in the middle, and this hole is hopefully, and we are very optimistic that it will be filled by g.Pype. So Christoph already mentioned it. g.Pype is now, our goal is that with g.Pype we can unify all those aspects I have just discussed on Python or in Python as a package which allows you to do your neuroscience experiments. Right, good. So let me now talk a bit from the bird's eye perspective about the architecture of g.Pype. So mainly it consists of two big parts. It consists of a backend. Backend means this is kind of a signal processing pipeline which is in the background. So it's that you cannot see anything, you're just feeding data into it. It's doing something and you get an output, right? And here we have some very common dependencies like NumPy, SciPy, but also the YoYo core, which is our proprietary data propagation framework, also in Python, right? And coupled to this backend, we also have a front end. So front end is everything you can see on the screen. It's everything that related to visualization, graphical user interfaces. And here we use Qt and PySet6 as a public dependency, which is also free, to render the outcomes in real time on the screen. So on top of that, you can use the backend and the front end and create your BCI or neuroscience application. And the goal is, as I already said, everything technical, everything difficult, from the very low level data propagation to the mid-layer node interfacing to the high level GUI abstraction layer. It's all covered by g.Pype, and g.Pype is providing you an extremely simple interface to just create your basic applications, but it also provides you a programming interface to, for example, derive from certain classes and create your own custom pipelines, right? Good. So we have a couple of highlights, and I just wanted to briefly mention them. So g.Pype per se is a free Python package. So it's already in beta state uploaded to GitHub and to Pype, so you can install it right away. And it's cross-platform, so it's compiled for Windows and for Mac. You can use it for both machines. I will also mention it, but maybe I should mention it now. So for Mac, we have two restrictions. So one of them is that the paradigm presenter, which has been always developed for Windows and will stay on Windows, is not available on Mac within g.Pype, but Windows can use it. And the g.Nautilus, which is based on the GDS, which is also a purely Windows-based g.tec kind of device acquisition service. It's also only available on Windows and not for Mac. So if you're not using g.Nautilus and not using Paradigm Presenter, but maybe you're using some other presentation tool using Python, and if you're using the BCI Core 8, you will be fine on Mac. So as you will see a bit today, but also on Saturday, we've tried our best to create g.Pype in a very modular design. So it just contains the building blocks you need for experiment, and then you just connect them and you run it, and that's it. yeah, it should be simple, user-friendly, and as I already said, you can easily adapt and extend the blocks, the classes you will find within g.Pype, just so they suit your needs. Of course, you can interface also third-party packages because, as I said, we don't want to compete. We want to complement. Feel free to use your custom processing block in g.Pype and use, I don't know, some other machine learning package you will find, or maybe you have developed to integrate it into g.Pype, right? And then very well, which kind of closes the circle from the free Python package on the top. So free is for development, for research, for testing. But when you want to go commercial, when you have your application you want to deploy and you want to sell, then it's on the one hand it's fairly simple because it's possible to deploy and to compile Python very easily. And here to especially deploy g.Pype applications, you would need then the g.Pype runtime, which allows you to, moving out from your development environment or from your script-based environment, really into an application environment. And here, I mean, of course, this is not free anymore, and you would have to get a license for that. But I think this is pretty much common sense. Right, so I have talked about some restrictions already, and to be fair, I have to mention 3 of them. So of course, we want to keep our interests safe. So we restrict g.Pype to be used with g.tec amplifiers. I also think that's quite understandable. And you can use BCI Core 8 and g.Nautilus for now. Might be extended in the future, but that's the current state. And if you want to go commercial, you need the g.Pype runtime. And I already mentioned that the Paradigm Presenter and the g.Nautilus are Windows only for now, but might be that this will be not changed. So you will ask, is it available already? So yes, it's on GitHub already. So feel free to go to github.com, find our account, g.tec-medical-engineering, and then you can see our repositories. So you just go to g.Pype, you can have a look, and also make sure that you follow g.tec on GitHub because it's very active in development right now. We have reached the beta state. So what you see today is the current state we have, but we will, of course, extend it in the future. We will do, we expect to need quite some bug fixing still, but the current state is already quite robust. And yeah, if you want to use it, just hit pip install g.Pype and you can use it. Right, beta status, I already mentioned that. And yeah, what's also important, so we focused on implementation first, and documentation is ongoing. So we will, we already have GitHub pages available, so you will find the link, but there it's just a skeleton still. So we will, as the time goes by, we will put more information into that. So in the end, the goal is that by the middle of this year, we have quite comprehensive documentation with all examples online. Right, and the g.Pype runtime I already mentioned is currently under development. So we have done feasibility tests, so that works pretty well. So if you're interested, feel free to reach out to our sales team. And if we have enough requests, we will speed up the development, but right now it's also planned for mid 2025. All right, so let me have a look. Good. I have a couple of slides more about the architecture and about the programming. I will just go very briefly through them, or actually kind of skip them because I will talk about them more on Saturday. But what you should know is that it's a node-based signal processing pipeline. So we have a couple of nodes, which are input nodes, output nodes, or input-output nodes, or I/O nodes. and they serve certain purposes, and it's kind of an inheritance pattern. So we have base classes, and as the purpose of a node gets specialized, it inherits from this base class. Good. Configuration, yeah, maybe. So if you're interested, this might be a teaser. I will talk more in detail about this on Saturday. Pipeline monitoring and logging, front end. Yes, I think we can right away go to the live demo because I have prepared a couple of scripts for you. Let me see, let me end the presentation first and then hop over to Visual Studio Code, which you can see hopefully now. Right, good. I have 3 examples which are using generated noise, so without any amplifier, but this should just demonstrate the usage of g.Pype. So this is a script which uses g.Pype to produce some pseudo noise with a noise generator at a certain sampling rate with a certain channel count and a certain variance. So first of all, after importing g.Pype as GP, you are creating the main application. This is the front end, gp.mainApp. You're creating the pipeline, gp.pipeline, and then you're creating all your nodes. So this is the source, signal source. It's a noise generator. Then we put this noise into a bandpass filter, which we create here using the SciPy package, the bandpass filter from 1 to 30 Hertz. Then we have a scope. So this is receiving the data from the backend and showing it in the front end, in the GUI. And we also have a file sync. So we want to store the data in a CSV file. So we have 1, 2, 3, 4 blocks, which we have created here. And then we use the pipeline P and we connect those blocks, right? So first we connect the source and the filter. So that means everything the source produces goes into the filter. And then we connect the filter to the scope. So everything the filter produces goes into the scope and is shown on the screen. And at the same time, everything which is produced by the filter goes into the sink. It's stored into a CSV file. Okay, and then, so this is the pipeline. Then we have to add the widgets to the main application. So if you're familiar with Qt, you know what a widget is. So this is basically an abstract concept of a graphical container showing something. A main application can contain various widgets in a certain arrangement that really is very flexible. And here we are adding a widget to the main application, and this widget is the scope. And then just for demonstration purposes, I already have a performance monitor, which kind of shows you the estimated resource demands of the pipeline. And I also add this widget monitor to the main application, right? So now this is, these lines are setting up our main application. And then I just have to hit pipeline.start, p.start. I run the application. So this is blocking. This is showing the main application. And then after the application has been closed, I stop the pipeline, right? So let me execute this. So here we are. This is our real-time scope showing the randomly generated data filtered from 1 to 30 Hertz over a course of 10 seconds, and then it's repeated. And down there, you can see the performance monitor, which shows you the estimated pipeline load in percent. So probably here, it's fairly high because I'm sharing my screen. So when I'm doing it without screen sharing, it's down there at maybe 4 or 5%. It's interesting how much resources screen sharing takes. Okay, good. And then, yeah, we can increase, for example, the sampling rate to 500 to, and the channel count to 64. So this was possible without screen sharing and Zoom. So let's see how it works under more demanding conditions. Yeah, so you can see it's very laggy. So we are almost 100% filled. Yeah, so that's not working with screen sharing right now. I've rehearsed it before my talk, and I was at about 20-25%. So yeah, again, interesting how much resources screen sharing takes. Good, because we have already prepared a real experiment. I just want to very briefly show you how to use, for example, keyboard markers as feedback. So let me execute this one. It's the very same pipeline. I have a noise source, but also I have a keyboard source. So I have a keyboard marker, which captures the keyboard kind of values. So each key has an associated value. And here we are. And this keyboard value is shown in the as channel 9 here. And I also have configured the scope to produce trigger markers whenever an arrow is hit, right? So I'm pressing now keys. You can see that the trigger signal changes, but also a marker is shown in the scope. And if I hit some other keys, you can see they're also shown, but the trigger markers do not react. Okay. So this is about keyboard feedback. And then I also have the paradigm presenter, which I also want to show you before I head over to Sebastian. So I'm doing it very briefly now. I know it. It might be a lot for those not familiar with Python, but I can again only refer to my second lecture on. Oops, sorry. Refer to my lecture on Saturday, where I will dive into the programming principles a bit more. Very interesting. So that also has to do something with screen sharing and the resource demands, because it was working like a charm right before my talk. Let me see. Yeah, anyways, so Sebastian definitely has a working example because he will not share the screen. We will do it with my webcam showing his screen. Yeah, so maybe on his machine we will briefly explain the paradigm presenter. Right, so I think I will mute myself now and Sebastian will take over. So go ahead.
All right, hello everybody. I swear I exist without the cap on as well. You mostly see me with the cap on, but there's hair under that, and there's an actual head under the cap as well. You can see here the paradigm still. So this is just an example presenter, which we will then be using. Maybe you can then remove the blur from your webcam, because right now there's still a blur, so they can't see my screen yet. In any case, we're going to run a paradigm, and this paradigm will have essentially 3 different stimuli. So it's going to have 2 different like checkerboards, which are very, very commonly used in neuroscience. And then there will be some stimuli of faces, and these will be from a data set we got from Duell, which is a quite famous neuroscientist from Israel. So in that case, thanks for him for these data. As we said, we will not be sharing my screen, so you will only be seeing what I'm seeing right now on the computer screen. And that is because Zoom takes up just tremendous amounts of resources. We're going to run a visual stimuli, and that visual stimuli is only presented for a very short period. You want the period to be exact, and Zoom will just jitter and will introduce some delay in that, and you definitely don't want that. So in any case, let me now go to the actual code. And yeah, it's only your screen that is being shared. So essentially what I'm going to do is run this script, and you will be seeing very, very soon the stimuli on my screen, and I will be counting whenever faces appear. Okay. You can also try it with me, because it's essentially like a cognitive task. You can count faces with me, and at the end you can put them in chat, and let's see how many you counted and how many it should be, because I will know the answer. We're gonna run the whole thing. It's gonna connect to the Nautilus, which I have on my head, and then we are basically good to go. It's just taking a little bit because it needs to compile everything. But now what do we see? We see here on the left side the EEG scope, and this is like literally and actually my EEG data. For example, when I'm now blinking my eyes, you can see a clear eye or EEG artifact. And here you have a little black box, which is the paradigm center. And once I'm starting the paradigm, I will maximize it. And then here there will be the displayed images. So now we're going to start here, click on start paradigm, and we're good to go. And now I have to actually concentrate and stop talking. Good luck. And now we're done, which means I can now close the whole thing. And now I can actually share my screen and show you the results. So let's see. I will now take over the screen share and replace Johannes in this case. And now you actually see my screen. So you see my little mouse moving, right? And we now see here in kind of the Explorer view, we see a bunch of files. And if you check the time, at least down here, it says 10:44. Here it says today's date, and then 10:40, which is just the file that we now created. I'm gonna copy that file name right there. And we're gonna now put it into a little evaluation script that Johannes has prepared, where we read in a CSV file and we plot the results. These are the channels that we're gonna be using or plotting. So these are literally the channels on my head. And we have, in this case, a T pre So this is kind of the time before each stimulus, and then a t-post, which is the time after the stimulus. And yeah, the rest is just a little fancy plotting, which you can easily do yourself. And we're going to be loading the file and then epoching it and then plotting the average of my brain responses. And there we go. So what do we see? We see 3 different lines in general for all the little channels, right? And we have 2 different shades of red. One is for this low frequency checkerboard and one is for the high spatial frequency checkerboard. And then we have a blue line, and the blue line is for the phases. The phases, as you might have noticed, are much, much, much less frequent in comparison to these other 2 like checkerboard stimuli. And as I told you, I was counting the phases. And by counting these phases, I am like putting a lot of cognitive effort into that, which creates a P300 response, or the classic P3. Okay. For this paradigm, this is always the case for me. I can show you a data set just that we recorded previously, both yesterday and just before the presentation today. It's always negative. And you can see this clearly negative deflection here, and then it goes up again. And this is especially pronounced for these like central and frontal regions, right? On the other hand, for the PZ electrode and for the more of the occipital regions, we have a clear negative deflection and positive deflection for our checkerboards. And this is because, especially back there at the visual cortex, we are extremely prone to these checkerboard images, these high spatial frequency images. That's also why checkerboard images are, for example, used in actual clinical research, because you just expect a very pronounced visual evoked potential. Now you could, of course, now that you have the data, you can then process it, put it into machine learning, put it into an EEG net, put it into whatever you want, and really investigate, okay, it does look different, but can be classified and all the type of stuff. You could now then also check yourself. Just for fun, I'm going to load the other file as well, just to show you that it does actually always look like this. So this is from today. We have one from roughly 1 hour ago, which I will now load. So just have to hope. Okay, there we go. So what you do not see probably is the little pop-up bar from Zoom always appearing on my screen, which is working against me. So now we're loading the one from 9:40 today. And again, remember this little shape here for the blue evoked potential. So for this phase stimuli. And lo and behold, it's there as well. It was there roughly 1 hour ago. It's there now. And even if I would be loading the one file from yesterday at 7 or 8 in the evening, it will also be there at that point, which shows just how reliable how reliable the whole system is if you just set up your program properly, if you have a good signal processing, a good hardware, and then in this case, we're running it all in Python. So it's very, very easily accessible as well. And that's basically it from my side. So I hand over again to Johannes.
Thank you so much, Sebastian. You're showing how reproducible our experiments are. So that's one key requirement. I'm always amazed. So you are reproducible. That's good. Your brain has a high level of reproducibility, but also luckily we are quite happy to see that with g.Pype and Paradigm Presenter and g.Nautilus and all this kind of stuff we put together has a high degree of reliability and reproducibility, as demonstrated by Sebastian just now. So I'm already at the end of my talk. I could talk much more, as I said. If you're interested in more details, please tune in on Saturday at 10:30, where I will continue. Otherwise, and I apologize, I've seen that my webcam has been frozen for while Sebastian was doing the experiment. So yeah, you have not been able to count the phases. Might be that on Saturday we will repeat it. So make sure to be there as well. Otherwise, I'm happy to take your questions and let me know, yeah, your thoughts.
Thank you very much for the demo. Shalini is asking, can you also plot EEG traces in Python as we have seen it in MATLAB before?
Exactly. So the script Sebastian was showing is based on Python. So of course you can just use matplotlib, which is for some reason called matplotlib. It has very similar features as MATLAB to plot any kinds of data, and this in particular also EEG traces.
Garrick is asking, do you have experience with Python React workspaces such as Bonsai? Are you using that or something else?
Not at all, to be honest. So it's quite recent that we moved to the Python domain, and we are still learning every day. We have now, not been able to use third-party visualization tools apart from Qt, which we have been using previously very successfully also with our C and C++ applications. And that's basically the visualization and graphical user front end we are using.
Zainab is asking, are there any courses regarding Python for neuroscience and neurotechnology that they should attend?
Yes, as far as I know, we are planning a Python for neuroscience masterclass, right? So that will be, I don't know the date, but make sure to stay in touch because there we will collect and come up with experts from the Python and neuroscience domain, and I guess it will be one day full of lectures just about this topic. Just muted. You're muted.
Helps to unmute. Somebody's asking if the g.Pype is available for public use and what are the license terms?
So the license terms are, we have created a license which is called g.tec non-commercial license. So it's free for non-commercial usage. So you can just use it. If you have a g.tec amplifier, you can use it and play around with it. But when you want to go commercial, then you have to purchase a deployment license and using the g.Pype runtime.
Garrick wants to know what you understand under the term block.
Block. Block is an element in a signal processing chain which is modifying the signal. So it has an input and it has an output. And whatever purpose this block has, it will modify the signal. For example, it could be just a high-pass filter, which just removes the lower frequencies or vice versa. So that's the abstract concept of a block.
Chandra wants to know for the g.Pype SDK, do users get the source code or only libraries that they can use for custom developments?
So there is, for some parts, it's closed source because we have, for example, to protect the code, protect g.Pype to be used only with g.tec amplifiers and stuff like this. But we have made as much as possible open source, especially the whole let's say the node principle, where you can use and where you can explore nodes in the g.Pype open source and see how they are implemented. For example, routers, filters, sources, sinks, and so on. And then you can create your own nodes and you can derive your own nodes customized for your purpose. And I also want to mention that we are, as I said already, we are actively developing it, but we are also integrating more and more blocks or nodes as the time goes by. So it will be populated throughout the year. So stay tuned.
And also keep in mind the advantages of open source, but there are also advantages of closed source. So a very good example is the firmware or the data acquisition pipeline from a biosignal amplifier. Because that's well tested, it's verified, it's validated, it has electromagnetic testing and everything is done. And by changing the code, for example, in the headset or in the data acquisition, you could produce, for example, ESD effects that you cannot really control, and then the radiation, for example, is too big, or the data transmission is not ideal and it gets interrupted. So if this would be open source, then people would actually destroy the real-time behavior, which is actually well tested. So it's much better to keep it protected. But of course, you can put in your own feature extraction, classification, your own algorithms. So this is all open source. Garrick wants to know, Can you do parallel processing with the pipeline?
You mean parallel in terms of multi-threaded? This is, as far as I know, possible at least on a single CPU. So we are using the multi-thread libraries provided by Python. So multi-core parallelism is not supported by Python at all, as far as I know. But our tests have shown that it's actually not necessary. So if we have one CPU core and use multiple threads on that core, that's by far enough.
Sign up wants to know, can we get the example files that you just showed?
Yeah, exactly. So they are actually on the public repository already. Let me check. They are. Yeah, you can have a look. And also, again, on Saturday, we will dive a bit more deeper into that.
Kerti wants to know, can we still work without hardware when we use g.Pype?
Yes, you can use with the source generator, which just produces random noise, which I just showed in my talk.
Then can we use g.Pype during the hackathon?
Good question. You can on your own risk, of course. As I said, it's not perfect yet. It's still in a beta state, so it might be that you run into problems if you're doing very sophisticated stuff. But of course, you can try it out.
But of course, there's also a Python API that you can use for the devices, or Unicorn or Nautilus or g.Pype. So this is of course also working for the hackathon. Are there any Jupyter files that the demo is using?
No, not yet.
Okay, thank you very much for the nice presentation. Very well
Thank
done.
you as well.